All right, thanks everyone for coming to our seminar for today. Today we have a visiting PhD candidate from the University of Lorraine in France, Elena Petri. She's a PhD student there. She's going to be telling us about hybrid techniques for estimation, state estimation, event-triggered observer design, and observer performance improvement. Elena is currently under the supervision of Romain Postillon and Dragan Nesic and Danielle Astolfi, and she received her Bachelor of Science degree in Mechanics and Mechatronics Engineering and a Master's of Science in Mechatronics Engineering from the University of Padova in Italy in 2017 and 2020, respectively. She performed a Master's of Science thesis at the University College Cork in Ireland between September 2012 and March 2020, and her research interests include observers, nonlinear systems, and hybrid systems. Thanks, Elena.
Thanks for the introduction. So, hello everyone, I'm Elena Petri, a PhD student at the Université de Lorraine, and I will present you this work which titled is Hybrid Techniques for State Estimation, Event-Triggered Observer Design and Observer Performance Improvement. That is a joint work with my supervisors, Romain Postillon, Danielle Astolfi, and Dragan Nesic, and was also in collaboration with Maurice Siemens and Vincent Andrieux. And in this talk, I'm going to present you some estimation problems. In particular, we want to design an observer in order to estimate the internal state of the system, X, that is unknown and we want to estimate, starting from the knowledge of the input U, the output Y, and the system model. And in particular, we will see hybrid observer, so observer that have both continuous and discrete dynamics. And why people are interested in hybrid observer? Well, there are three main reasons. The first one is like when the system plant is an hybrid system. So in this context, makes sense designing a hybrid observer. A second group is, even if the plant is designed in continuous time, maybe it makes sense to use hybrid techniques in order to improve the estimation performance of an observer. And the third category is when the system and the observer are not collocated in the same place. And therefore, there is a network in between them and the data are transmitted over the network. And for this reason, makes sense describing the observer using hybrid techniques. And I will divide the talk in two parts. The first part, consider this work, the title is Event-Triggered Observer Design for Linear System, that enter in the third group of the one that we saw before. So when there is a network between the plant and the observer. And this work has been presented last year at the CDC. In the second part of my talk, I will present you another work which title is Towards Improving the Estimation Performance of a Given Nonlinear Observer, a multi-observer approach that enter in the second category before, where we use hybrid techniques to improve the estimation performance. And this work has been accepted for presentation at the next CDC. So this is the outline of my talk. I'm done with the introduction. I will first focus on this event-triggered observer design for linear system work. And after that, we will see the observer performance improvement. And finally, we'll conclude the presentation. So for this first part, I will first introduce the problem, and then we will see the design procedure and the hybrid model. After that, we see the main results that we prove in this work, and we see how the event-triggered observer works in a numerical example. Finally, I will conclude this first part of the talk. So for this talk, we consider the setting where the plant and the observer are not collocated in the same place. Indeed, there is a network between them. And for this reason, the observer does not know the wall of Y, but only a sample version, Y bar. And this sample version of the output can be generated based on time on a time trigger strategies, or based on the real value of Y on an event trigger strategy. And in particular, in this work, we consider an event trigger estimation problem, where our objective is to design an event-based triggering rule implemented by a smart sensor in order to decide when the output data Y need to be transmitted from the plant to the observer via the network. And we assume that the observer has access to the input U continuously. And many people work on event trigger estimation problem in the literature. In particular, numerous work consider stochastic setting. However, we consider deterministic setting, and two main approaches are present in the literature. The first one consists in implementing a copy of the observer in the sensor, and therefore it uses the state estimate information in order to decide when a data needs to be transmitted from the plant to the observer. The drawback of this technique is that it may require significant computational capability on the sensor. Another approach present in the literature is the absolute threshold triggering rule. It simply consists in comparing the last transmitted output value and the current output. And when their difference is bigger than a constant, it triggers a transmission. The drawback of this technique is that it may require a lot of transmission. So in this work, we will try to take the best out of the two. In particular, we want to reduce the number of transmission compared to the absolute threshold triggering rule without requiring significant computational capability on the sensor. Indeed, we will ask the sensor to have enough computation capability only to run a scalar filter. And we consider linear time invariant systems that are described by this equation, where x is the state of the system that is unknown and we want to estimate. U is the input and y is the measured output. And we assume that the pair AC is detectable. We follow an emulation-based approach. And therefore, we first design the observer ignoring the communication network. And we design a linear Leuenberger observer that has this form here, where x hat is the state estimate produced by the observer. And the observer is a copy of the system plus a correction term. And this correction term depends on the gain, L, that is designed so that the matrix A minus LC is U-width, which is possible since AC is detectable. In a second moment, we consider the network. And therefore, the observer does not know the wall of Y, but only a sample version, Y bar. And its equation are modified as you can see here. So the only difference is that we have Y bar here instead of Y. And the sample version of the output is generating using a zero order roll device between transmission. Therefore, Y bar is kept constant between transmission and is updated when a transmission occurs, as written here, where Tk are the transmission instants. And we define the state estimation error as the difference between the real state, x, that is unknown and we want to estimate, and the state estimate of the observer. And this is the dynamic of the estimation error, where this E is the sampling induced error, so the difference between the last transmitted output value, Y bar, and the current output, Y. And since the matrix A minus LC is U-width, we know that there exists a quadratically opponent function B, define a C transport big C, where P is a symmetric positive definite matrix, so that this inequality here holds. And from this one, we see that in order to don't destroy the stability, we need to control the norm of E. And for this reason, in the literature, people propose the absolute threshold triggering rule. And in particular, they compare the last transmitted output value and the current output, and they evaluate the difference. So this sampling induced error E. And when this difference is greater than a constant, a transmission is triggered. The problem of this technique is that it may produce a lot of transmission. Therefore, this is the triggering rule that we propose. We propose to transmit a new output data when this rule here is satisfied, this condition is satisfied. So we compare the net induced error E, and when this quantity is greater than a constant, as happened in the absolute threshold triggering rule in the literature, plus this additional term, we trigger a transmission. And this additional term, we have this variable eta, that is a scalar filter as described here, and where C1 and C2 are design parameter, positive design parameter. Sigma here is another design parameter that note that can be selected equal to 0. So we can recover the absolute threshold triggering rule already present in the literature. Epsilon here is another design parameter, and it's important that it has to be selected strictly positive in order to avoid the Zeno phenomenon that occurs when two output data are transmitted in the same time instant or immediately one after the other. Then we model the overall system as an hybrid system. And to do that, we first define the overall state of the system Q in this way. So we have the system state X, the state estimation error Xi, the sampling induced error E, and this additional scalar variable eta. And we use the flow and jump set to define when a data need to be transmitted from the plan to the observer. In particular, when this condition is satisfied, we don't need to trigger a transmission. So we are in the flow set C, and the hybrid state evolves according to this flow map here. Conversely, when this condition is satisfied, means that the observer needs a new output data to perform the estimation. And so we are in the jump set D, and the hybrid state is updated according with this jump map here. And we can now see the main result of this work. And in particular, since the matrix A minus LC is your width, we know that there exists a quadratically Lyapunov function B, defined as C transport peak C, where P is a symmetric positive definite matrix, so that this inequality here holds in absence of network, which means that the Lyapunov function is converging with a decay rate of alpha. In this work, we prove that for the proposed event trigger observer, we have that this inequality here holds, which show that this new Lyapunov function, that is the previous one, plus a term that depends on this additional scalar variable, is converging and is decreasing with a decay rate alpha bar that can be selected between 0 and alpha. Therefore, we can tune the design parameter in order to obtain the same decay rate of the Lyapunov function that we have in absence of network. And this shows a practical stability property. Indeed, we will converge to a neighbor of the origin. And we have this ultimate bound here, nu, that represents the size of the neighbor of the origin where we will converge. But this ultimate bound nu can be selected arbitrarily small. However, the smaller we want this nu, the higher is the number of transmission required typically. And note that this Lyapunov inequality implies that the estimation error C is converging to a neighbor of the origin. Indeed, we have this lower bound here on the Lyapunov function B. Moreover, in an even trigger estimation problem, it's really important to guarantee a strictly positive minimum time between any two transmission over the network. And I recall that this is the triggering rule that we propose. Therefore, we need to estimate the time that it takes from gamma norm square to grow from 0, that is the network-induced error value E after a jump, so after a transmission, to epsilon that comes from the triggering rule. And we see that to have this strictly positive minimum time between any two transmissions, we need that the time derivative of E is bounded. For this reason, we restrict the flow and jump set in this way, that are the previous flow and jump set C and D, intersected by this set, which is simply a set where the time derivative of E is bounded by an arbitrary large positive constant M. And we prove in this work that for any M, any solution pair of this new hybrid system has a dual time tau M, defined by this equation, which means that the time between any two transmission over the network is always greater or equal than this time here. And from this expression here, we see why it's needed that the epsilon is strictly positive. Moreover, we prove that the proposed event trigger observer allowed to stop transmitting when a new output data is not needed to perform the estimation. And this is really an advantage against trend-trigger strategies that always trigger a transmission even when it's not needed. And this happens in particular when the output remains in a small neighbor of a constant for all future times. And we can now see on a numerical example how the proposed event trigger observer works. And in particular, we consider a lithium-ion battery that is described by this electrical circuit and by this equation. And the internal state of the system that is unknown and we want to estimate is the voltage of this RC circuit and the state of charge of the battery. The input of the system is the current I bat, and the measured output is the voltage V bat. And we consider a PHIV current input, which is typical in plug-in hybrid electrical vehicles. And we obtain this output voltage here. Then we evaluate the state estimation error in both states. And from these plots, we see that both states practically converge. Indeed, the state estimation error are converging to a neighbor of the origin. And if we zoom it, we see that we have this ultimate bound of the convergence that is very small for both states, is of the order of 10 minus 3. That is good for the application. Then we also evaluate the time between any two transmissions over the network. And for this example, we obtain a dwell time of 0.227 seconds, which means that the time between any two transmissions over the network is always greater or equal than this time here. Moreover, from the plot, we see that when the output remains in a small neighbor of a constant, like happened in this time interval and in this time interval, the time between any two transmission grows, which means that no transmission are triggered for this whole interval. And finally, we evaluate Grandson simulation to evaluate different choices of the design parameter. And in particular, we select the configuration where sigma was equal to 0. So when we recover the absolute threshold triggering rule already present in the literature. And in this example, we obtain that with the proposed event trigger observer, we have less than half transmission compared to the absolute threshold triggering rule, without a big impact in the ultimate bound of the estimation error. So in this first part of the talk, I present you an event trigger observer design for linear system, where we design a dynamic triggering rule that does not require significant computational capability on the sensor. We prove a global practical stability property of the estimation error, and we show that the system has a dual time, which means that the time between any two transmission over the network is always greater or equal than a positive constant. Moreover, we show that the proposed event trigger observer allows to stop transmitting when a new output data is not needed to perform the estimation. And this happens when the output remains approximately constant. And if you're interested in more details about this work, this can be found in this reference, event trigger observer design for linear system, that was presented last year at the CDC. Moreover, we extend the result of this work, considering general nonlinear system and nonlinear observer. So both the system and the observer are described by nonlinear equation. And we also consider a decentralized scenario, where there are n independent smart sensors, and each sensor decides when to transmit its own output data to the observer, independently from the other. And the extension, this extension, is in a work which title is Decentralized Event Trigger Estimation of Nonlinear System, that is submitted to Automatica. So I'm done with the first part of the talk. If there are some questions on this event trigger observer design, I will be happy to answer.
What's the effect of noise on the performance?
Yes, in this first work on linear system, we didn't consider noise. While in the extension, there is a part that consider noise. And in this case, it's important that if we have a bound, we have to consider a bounded noise, and the epsilon does not have to be only strictly positive, but has to be enough bigger in order to don't trigger a transmission only because of the noise, but we need to have that the difference between the output, the last transmitted output and the current output is enough to trigger, good enough to trigger a transmission. So we have to increase that epsilon, so have a bigger, this implies that the ultimate bound of the convergence will be bigger, but in any case, when there is the noise, it cannot converge perfectly to 0, there is always a bound. So you just need to know the bound on the noise. And
Do you consider the transmission of the between the U over the network or just the output?
in this first work was only the output. In the extension, not from the beginning, but there is a subsection where we say that we can also transmit the input over the network with a similar triggering rule. And in this case, we need the condition of the epsilon also on the input transmission. And the proof is the same. You just need to be more careful on the details. And we can also have a triggering rule on the transmission of the input.
So for the current case, I do think it's possible to get the global stability rather than the 5%. This answer.
Sorry, I don't really understand.
For the current version, you only got the practical stability rather than global exponential and symptotic stability. So do you think it's possible to remove the output?
In case is not in our case, because to have that, we need the all works in the literature that obtain a convergence without a ultimate bound are work that implement a copy of the observer in the sensor. And so, especially if the system dimension is really big, we need a sensor that have a high computation capability, which is what we want to avoid in this work. And to avoid that, we have an ultimate bound. And we cannot converge perfectly to the origin. I can continue with the second part. Thanks for the questions. So the second part, we use hybrid techniques for an observer performance improvement purpose. And for this part of the talk, I will first introduce the problem and give the problem statement. And after that, we will build step by step the hybrid multi-observer scheme that we consider. Moreover, we will prove the stability guarantees, and we will see on a numerical example how the proposed hybrid multi-observer improve the performance of a high-gain observer used to estimate the state of a Van der Poel oscillator. And finally, I will conclude this part of the presentation. So also in this case, we consider estimation problem. So we want to design an observer to estimate the internal state of the system X, starting from the knowledge of the input U and the output Y and the system model. And there are many works in the literature that design observer to guarantee a convergence property of the estimation error. However, it's very difficult to tune the observer in order to obtain a fast convergence, a small overshoot, and be robust to measurement noise and disturbance. Indeed, there is typically a trade-off between these properties. And ideally, we would like to design an optimal observer, but solutions are available only for specific classes of system, like for example, the Kalman filter in the context of linear system when the noise has a particular form, or is very hard for a general linear system. And there are some work in the literature to try to improve the performance, but solutions are available only for specific classes of system, like for example, the linear system or the eigen observer, or focus only on some specific properties, like the robustness to measurement noise, and or to reduce the undesired effect of the peaking phenomenon. Another work in the literature is the uniting observer, where the author proposed to switch between a local and a global observer in order to exploit the good properties of both of them. However, this is not always easy to implement. Therefore, we feel that there is a really strong need to have an estimation scheme that guarantees good estimation performance. And in this work, we propose a new framework that we believe that has not been addressed yet in the literature. And our solution consists in considering general nonlinear system and assume that we know how to design an observer for this system that has some stability guarantees. And this can be done with one of the many available techniques in the literature. And after that, we redesign the observer based on a multi-observer and using hybrid techniques in order to improve the estimation performance while preserving a stability property. Our contribution is that we design a multi-observer that aims at performance improvement. And we guarantee a convergence property of the estimation error. We apply our approach to a general nonlinear system. And we show on a numerical example that the proposed hybrid multi-observer highly improves the performance. So we consider a general linear system that is described by this equation, where X is the internal state of the system that is unknown and we want to estimate. U is the input, P is an unknown disturbance input, Y is the measured output, and W is the measurement noise. And we assume that we know how to design an observer for this system that has this general form, where the state estimate of the observer is denoted by X at 1, where we use the subscript 1 because this will be the first element of the multi-observer that we will build in the next slides. And the dynamic of this nominal observer depend on this term here, so on the gain L1 that multiply the output estimation error, so the difference between Y and Y at 1. And we define the state estimation error for this nominal observer, E1, as the difference between the real state, X, and the state estimate of this nominal observer, X at 1. And we make an assumption on the stability property of this nominal observer. But to do that, we first need to define a perturber version of the aerodynamic in this way, where D here represents a perturbation. And this is the assumption that we make. In particular, we assume that this two Lyapunov inequality holds, which means that there exists a Lyapunov function V that is positive definite and randomly unbounded, and that is decreasing. And this two Lyapunov inequality implies this inequality here in terms of estimation error, which means that the estimation error of the nominal observer is converging to a neighbor of the origin. Indeed, this first term here is a KL function that go to 0 as the time go to infinity. While this other term here represents the ultimate bound, so the size of the neighbor of the origin where we will converge. and depend on this disturbance input B, measuring noise W, and the additional perturbation D. And this input to state stability property guarantee a robust stability property of the estimation error, and is satisfied by many observer design techniques in the literature. However, it not always guarantees satisfactory performance in terms of convergence speed or noise disk rejection. Indeed, it typically is very conservative. Therefore, our objective is to do an hybrid design of the nominal observer that aim at improving its estimation performance while preserving an input to state stability property. And we can now build step by step the hybrid multi-observer scheme that we propose. So we start from the system and the nominal observer that we already saw in the previous slides. And in order to improve the performance of this nominal observer, we add an additional dynamical system in parallel to the nominal one. And each of these systems produce a state estimate. And with all these systems together, we build a multi-observer where each element is called mode for the sake of convenience. And each of these additional modes has this form here that, as can be seen, is the same structure as the nominal observer, where the only difference is in the gain, LK. And it's important that we don't need any convergence guarantees for the estimation error produced by this additional mode. Therefore, we have full freedom on the selection of their gain, compared to the nominal observer where we require an input to state stability property. And we define the state estimation error of this additional mode as the difference between the real state and the state estimate of this mode. And note that since we don't ask any convergence properties for this mode, we have that this estimation error may converge, but may also diverge. We don't know a priori. And we have a lot of flexibility in the number of additional modes that we add in parallel to the nominal observer. And we have also full freedom in the selection of their gains. Therefore, a question that may arise is how to select these gains. And we are still investigating on that, but we believe that this should be done on a case-by-case basis because it's highly dependent on the structure of the nominal observer. In particular, in the case of a high gain observer, where the nominal gain typically is really big, and this implies that the estimation error will be very sensitive to measurement noise. And an option is to select the additional gain smaller than the nominal one, in order to try to be more robust to noise. But in other contexts where we have no prior intuition on how to select the gain, we can just pick them in a neighbor of the nominal one, or just scaling the nominal one by some factors. And so we are in this condition where we have this multi-observer that produce n+1 state estimate. And we need to evaluate the performance of each mode of the multi-observer in order to select one mode at any time instant. For this reason, we have designed some monitoring variables, one for each mode. And these monitoring variables are used to evaluate the performance of the mode. And ideally, we would like to design them based on the information on the estimation error. But however, we cannot do that because the real state X is unknown. So we cannot use the state estimation error to design the monitoring variable. Therefore, inspired by some techniques in the literature, we designed the dynamic of the monitoring variable based on the output estimation error. So the difference between Y and Y at K. And this is the dynamic that we propose, where we can see that we have a first term here that depends on the output estimation error. Where we have another term here that considers the correction effort of the observer, also called latency in the literature. And lambda1 and lambda2 are two positive design parameters, while this nu is a positive parameter that has to be selected between 0 and alpha. Where I recall that alpha is the decay rate of the Lyapunov function that we have in the input to state stability assumption of the nominal observer. And if we solve this differential equation, we obtain this expression here at the end of the slide, which show that these etas represent a cost for the mode. So we are in this condition. We have this multi-observer that have n+1 state estimate, and we have a monitoring variable to evaluate the performance of each mode of the multi-observer. So we need to design a selection criteria in order to select one mode to look at any time instant, based on the information that we have from the monitoring variables. And since the monitoring variables give us the evaluation performance in terms of cost, we have to select the one that minimizes its monitoring variable, which means that we will minimize the cost. And we use a signal sigma to indicate which mode is selected at any time instant. And we denote by x at sigma the state estimate produced by the proposed hybrid multi-observer, and with eta sigma the corresponding monitoring variable. And this is the rule that we propose. In particular, when there exists at least one mode of the multi-observer that has a monitoring variable smaller than eta sigma, means that there is one mode of the multi-observer that is performing better than the mode that we are currently looking at. Therefore, we need to switch the mode we are considering. And so the signal sigma need to be updated according to this equation that take the one with the minimum eta, so the minimum cost. And note that this is an inclusion. Indeed, it's possible that two modes of the multi-observer have the same value for the monitoring variable and are both the minimum. And in this case, we just pick one of them. The problem of this rule is that it may produce infinitely fast switching. Therefore, we modify the rule in order to introduce this additional parameter epsilon in order to switch only when the minimum eta k is sufficiently smaller than eta sigma. And the rule is the same as before, just we add this epsilon here. And when we switch the mode that we consider, we propose two possible reset rules. The first one is called without reset, which only consists in updating sigma, so only consists in changing the mode of the multi-observer we are considering. Therefore, at any switching time, the state estimate and the monitoring variable of the nominal observer, as well as the one of the additional dynamical system, are not modified. Conversely, we also propose another reset rule that is called with reset, which consists not only in updating sigma as before, but also to reset the state estimate and the monitoring variable of the additional dynamical systems, not the nominal observer, to the updated value x at sigma and eta sigma. And the intuition behind it is like that the x at sigma and eta sigma are the best, the one of the best mode of the multi-observer according to this rule. So we can use their information and share it to the other in order to reset the others, in order to hopefully further improve their performance. Therefore, at any switching time, the state estimate and the monitoring variable of the nominal observer are not modified, while we update the state estimate and the monitoring variable of the additional dynamical system to the updated x at sigma and eta sigma. And this is the final block diagram that we obtain. So to recall, we have a system where we want to estimate the state, and we have a nominal observer that we have guarantees that is converging, but it does not have really good performance. And to improve this performance, we add n additional dynamical system in parallel to the nominal one. So we built a multi-observer that produces n+1 state estimate. We design a monitoring variable for each mode of the multi-observer in order to evaluate the performance. And based on the information given by this monitoring variable, we select one mode at any time instant. And compared to the block diagram that we saw before, here we have these dotted lines that are used when the case with reset is implemented. We can now model the overall system as an hybrid system using the formula of Goebel, Sanfelice, and Teel. And we first define the overall state of the system in this way. That is the system state x, the state estimate of all mode of the multi-observer, all the monitoring variable, and this signal sigma that tells us which mode we consider at any time instant. And we use the flow and jump set to decide when we need to switch the mode we consider. In particular, when this condition is satisfied, so when all modes of the multi-observer have a monitoring variable that is greater than epsilon tan eta sigma, which means that the mode that we are currently looking at is the best one because it's the one with the minimum eta, we don't need to switch. So we are in the flow set C, and the hybrid state evolve according with this flow map F that is defined in the paper using the equation we saw in the previous slides. Conversely, when this condition is satisfied, which means that there exists at least one mode of the multi-observer that has a monitoring variable eta k that is smaller than epsilon tan eta sigma, which means that there is one mode of the multi-observer that is performing better that the one we are considering according to our criteria, we need to switch the consider mode. So we are in the jump set D, and the hybrid state is updating according with this jump map G that is defined in the paper using the equation we saw previously. And we can now see the main result of this work. But to do that, we first need an assumption on the output map. And I recall that this is the output map of our system. And in particular, we assume that this inequality here holds, which is not a strong assumption. Indeed, it holds in the really common case where the Lyapunov function B, that from the input to state stability assumption of the nominal observer, is quadratic. And when the output map H is globally Lipschitz. And this is the main result of the work. In particular, we proved that the state estimation error of the nominal observer, as well as monitoring variable, and also the state estimation error of the proposed hybrid multi-observer and its monitoring variable are converging to a neighbor of the origin. Indeed, we have this first term here. It is a KL function that go to 0 as the time goes to infinity. And we have this other term here that represents the ultimate bound of the convergence. So the size of the neighbor of the origin where we will converge, and depend on this disturbance input V and on the measurement noise W. And note that this is a two-measure input to state stability property. Indeed, the KL function depends on the initial condition of the state estimation error of all modes of the multi-observer, and also on all the monitoring variables. While we prove on the left side of the inequality, we have the state estimation error of the nominal observer and the one of the proposed hybrid multi-observer scheme and their monitoring variables. And the proof of this theorem is based on a Lyapunov function that is given at the end of the slides for suitably selected design parameters C1, C2, and C3. And we can now see on a numerical example how the proposed hybrid multi-observer work. And in particular, we consider this system here, that is a van der Poel oscillator, where the matrix A, B, and C are given here. And the nonlinear function C is this one. And we consider this measurement noise for the simulations. And we design a nominal high gain observer to estimate the state of the van der Poel oscillator that has this form here, where you can see that is a copy of the system plus a correction term. And this correction term depends on the gain L1, which is defined equal to this capital H1D, where D is designed such that the matrix A minus DC is Hurwitz with eigenvalue in -1, -2, while this capital H1 is a diagonal matrix with H1 and H1 square in the diagonal, where this H1 is the high gain design parameter. And to satisfy an input to state stability property, and so to have guarantees that the estimation error produced by this nominal high gain observer is converging, this high gain design parameter has to be selected really big, was equal of 200 in this example. And having this gain so big implies that the estimation error will be really sensitive to measurement noise. And in order to improve the performance of this nominal observer, we add n equal to 4 additional modes in parallel to the nominal one. And these additional modes have the same structure as the nominal one, where the only difference is in the gain L case. And to modify the gain, we modify this high gain design parameter HK. And since the nominal one was really big, we reduced the nominal one and we selected H2 equal to 20, H3 equal to 1, H4 equal to 0, and H5 equal to -1. And note that for all these choice of high gain parameters, we have no guarantees that the estimation error produced by this additional mode is converging. And we don't have guarantees that an input to state stability property is satisfied for these modes. However, we ran some simulation and we saw that the first two choices produce a converging observer, converging estimation error, while the other two no. And we run and compare the result that we obtained from the nominal observer and the one of the proposed hybrid multi-observer in the case without reset. And we can see from the first plot that the state estimation error of the nominal observer is really bigger compared to the proposed technique in the case without reset. And the same on the monitoring variable. It is very difficult to see the red line in this plot. And to appreciate the difference and the improvement, we can zoom it. And we can really see that there is a big difference on the amplitude of the norm of the estimation error and the monitoring variable with the proposed technique. And the last plot shows the linear sigma, so tell us which mode of the multi-observer is selected at any time instant. We then compare the result that we obtain with the nominal observer with the proposed technique in the case with reset. And also in this case, it's very difficult to see the blue curve, so the one of the proposed technique compared to the nominal one. And we appreciate the improvement, the difference when we zoom it. And looking at the last plot, it's really interesting that in this case, when the case with reset is implemented, the fourth mode of the multi-observer that has a gain equal to 0 and was not converging on its own is selected for a big amount of time. And this helps to improve the performance. Finally, we compare the result of the proposed technique in the case without reset with the case with reset. And these are the results that we obtain in terms of norm of the estimation error and the monitoring variable, so the cost. And for this example, it looks like that the case with reset is a bit better than the case without reset, particularly in terms of norm of estimation error at the end of the simulation, and on the monitoring variable on the cost in mainly the whole time of the simulation. I can now conclude this part of the talk, say that in this work, we design a hybrid multi-observer that aims at improving the estimation performance of a given nominal nonlinear observer. And to do that, we add an additional dynamical system in parallel to the nominal one, with the same structure as the nominal one, but with a different gain. And it's important to recall that we don't require any convergence properties for these additional modes. So we have full freedom on the selection of their gain. And we prove a two-measure input to state stability property of the estimation error of the proposed hybrid multi-observer. In the future, we plan to give an analytical proof of this performance improvement. We want also to give an analysis of the hybrid time domain. Moreover, we would like to generalize this approach to other types of observers. And if you are interested in more details of this work, this can be found in this reference towards improving the estimation performance of a given nonlinear observer, a multi-observer approach that has been accepted for presentation at the next CDC. I will now conclude the whole talk saying that in this talk, I present you two problems where we use hybrid techniques to solve two estimation problems. In the first part, we saw an event trigger observer design for linear system, while in the second part, we see how we use hybrid techniques and the multi-observer to improve the estimation performance. Thank you for your attention.
Thanks, Elena. Any questions for Elena, either from in-person participants or anyone online? Yep, just got a question from Ian.
Hi, Elena. Thanks for a fantastic talk. And again, yeah, sorry I wasn't able to be there in person. I hope you're enjoying your visit to Sydney nonetheless. I had a question for the second part. You've got these kind of multiple potential observers and you're switching between them. Have you considered, or would it be useful to consider, instead of switching, to blend the predictions from two or more observers into the final state estimate?
Sorry, I didn't really understood instead of switching.
Yeah, so currently, from what I understand of your current design, you're switching, so the X hat that you produce as the state estimate is just the X hat from one of the n+1 observers, right?
Yes.
I was wondering if you've thought about whether it would be useful, instead of just switching to one of them, you could take, let's say, I mean, a simple thing would be to take a number of the X hats and take the average of them, for example, something like that.
In this case, this is not a really good idea because we don't require any convergent property of the estimation error for the additional modes. So we can maybe have one of them that is diverging. And in this case, if we average them, maybe this is really big, really far away, and we have worse performance. And to have an average one, maybe we should require convergent properties also on the additional mode, But to guarantee an ISS property, typically is really conservative, so does not really help to improve. Well, if we take only one of them, we are sure, thanks to the eta, that they are good.
Right. I mean, so I understand you don't want to average all of them, but for example, you could just average the subset of them which have an error below a certain threshold or something like that, right? Would that make sense?
These, yes, if there is more than one that has enough small error in terms of output, because it's the output estimation error, the only thing that we can actually use to choose them. Yes, we can average them, and this is a good idea. We didn't think thought about that, but thanks for it.
No worries. Yeah, thank you.
Any other questions for Elena? Yeah.
So in your example, we saw that the fourth mode was selected a lot, even though that was not converted, right?
Yes.
Can you comment a little more on why you say the performance gets better even though it's a not converted mode?
Yes, because that mode was as a gain equal to 0. So we are actually having the observer in open loop without a correction term. And the fact that we are selecting, thanks to the reset, every time that there is a switching, we can say it like the initial condition of this float time, so the continuous time is kind of resetted. So we are improving all the modes. And the one with a gain equal to 0 was not converging, but was not diverging because it has an eigenvalue equal to 0. And if we reset it to a smaller error, thanks to the information given from the others, this reduces error. And all the others, when you have a gain that is different from 0, that multiply y minus y hat, the gain multiply the measurement noise. So there is always a bound for the noise. And while the one with a gain equal to 0 does not amplify the noise because it's not multiplying the noise. And if, thanks to the other, we reset it to have an error that is smaller than the ultimate bound due to the noise of the other, this improves the performance. And because actually the error that you obtain at the end is smaller than the others, thanks to the reset. So thanks to the information that the other gave him after some resetting. I hope I was clear.